Hello, welcome to another Midnight Maths video. In this one we'll be talking about Riemann sums and the definition of a definite integral. I won't be going over all the types of Riemann sums here, but I will show how one type of Riemann sum in particular leads to the definition of a definite integral. This not only has computational importance, but also conceptual importance of what the integral is really doing behind the scenes. So let's start with this approximation here of the area under a function. We can see that we've got n equals 4 rectangles. So we've got 4 rectangles, and each of them are 3 apart. And we're going from a equals 0 to b equals 12. And now each of these are 3 wide, and let's call this width delta x, because it's going to be the same for every single rectangle. That seems to be a sensible decision. So this is 3, and this length is 3, and so on. Now, to find out this approximate area, which I'm going to shade in green, it's really this area plus that area plus that area plus that one. So we've got to add up all the areas of the rectangles. So let's start with the first one. Well, we already know the length, but what about the height? Well, you can see here that it's actually touching the function, right? Over here at x equals 3. And so that means this height, by definition, is f of 3, right? F of 3 gives you this distance between the x-axis and the point associated with that function. And it's the same for all these other rectangles. They all touch the function. So the area of the first rectangle then will be f of 3 times delta x, right? Simple enough. Now we've just got to add all the other ones. This one right here, for example, it's got a height of, you guessed it, f of 6. So the height right here is f of 6. And that point is 6 comma f of 6. So we would have to add another f of 6 plus delta x. And we do the same for the other two. So we get f of 9 plus delta x, and then f of 12 delta x. Now, this is great and all, and we can actually, since these delta x's are the same, we can factor them out. And we get something that looks like this, where we're just adding all of the function values, and then we're going to have this delta x just kind of tacked at the end here. So now, this is great. I mean, we got an approximation. It's better than nothing. But what if we wanted to get a little better approximation? What would we do then? Well, we'd have more rectangles, right? And maybe I'll draw a rough sketch of f again. And it looks something like this. If we had more rectangles, then maybe, for example, our rectangles might look something like this. We get even more rectangles, and so on. And you can see that this is better than what we have over here. So now the question is, what if we made n, for example, what if we made it 10? How would we do that? Well, we have to split these up again, and then we have to find a certain value for delta x, and then find all of these function values, and then add them all together. Let's not write all of that down for n equals 10, because it'll quickly get cumbersome for even bigger numbers. Like if you want n equals 20, it won't work. So maybe let's try and generalize this formula for any a, b, and n. Then we can just plug in whatever values, and we can get however large n that we want. So the tricky part really is this sum here, because the number of terms in the sum depends on your value of n and what your a and b values are. Let's see if we can write this as a more general sum. And we're going to start at k equals 1, and k is our index, but it's also going to be the number of rectangle. So it's going to be our kth rectangle. And so if we can figure out, using something involving k over here, what the area of the kth rectangle is, like the first one or the second one or the third one, then we can just add them all up. And we would have to end at n. right? Because there are n rectangles. So you have to add from k equals 1 to n the area of the kth rectangle. So this is the mathematical equivalent of what I said in the beginning of the video, where we have to add all 4 of these rectangles up. So let's really start to express this mathematically. So we know that the width is just delta x the entire time, and that doesn't change. So I'll write that over here. But then it's going to be multiplied by some height value, right? So what is the height of the kth rectangle? Well, it's going to be f of something, for sure. We know that, right? And, well, what is the x value that we take f of every time? Well, we go in multiples of delta x, starting from a, right? We start at a equals 0, and then we add 3, and then we add 6, and then we add 9, and we go all the way to 12. And let's sort of redraw this number line here, where instead of writing these numbers, I'll write it in a slightly different form. So here, we start with a, and then we're adding a single instance of delta x. And then we're going to add 2 delta x to a, and then we're going to add 3 delta x to a. And so we're essentially stepping by delta x on this x-axis every time for the kth rectangle. And note that this 1, it is for the first rectangle, and we add 2 delta x for the second rectangle, and 3 for the third rectangle, and so on. And so for the kth rectangle, we can say it's a plus k delta x, right? Because we step k times. Now, one more thing that we need to figure out is what is our delta x exactly in terms of our a, b, and n? Because we could figure that out pretty easily from the diagram that I drew, but what if I gave you, for example, a equals 0, b equals 12, but n equals 6? Then what's delta x? Well, we want to split. Each rectangle has to have equal width, right? And so we're going to start with the entire distance, this distance here, and that distance is b minus a, right? So we take this entire distance and then we split it in n pieces, and so we divide by n. So in this example, we had a total distance of 12, and then we split it into four pieces, and we ended up getting 3 for each piece. So we know that delta x is b minus a over n. And you can verify that this does indeed give us our delta x, which was 3 for this specific case using our values b and a. So this is pretty cool. Now, for any value of a, b, and n, as long as we have a function that we can plug into, we can find a Riemann sum for it using this cool little summation notation. But let's take it one step further. We know that large values of n will give us a good approximation. Well, why not just go infinitely large, right? So this is really the key here of this whole thing. This is where calculus really sort of makes its mark, so to speak. We're taking the limit as n goes to infinity. And so as you get infinitely many rectangles and your delta x shrinks, right? Because we go back to our formula for delta x. If n goes to infinity, if this number gets really big, then delta x is going to get really small, right? And so your n is going to get really big and your delta x is going to get really small, but if your limit approaches something, then we call that a definite integral between a and b, and we write it like this. And so we're going from a to b, right? And n is really going to infinity, so n no longer appears in our notation. And then this delta x that you see right here became dx at the end. When we took the limit, delta x became really small, and now we get dx. And you saw this when we did the derivative. For example, we could approximate the derivative with delta y over delta x. But then if you shrink this to infinity, then you get dy dx. So it's the same sort of notation here. And then, of course, our function is f of x, and we've got that over here. And so this is how we define our definite integral. Now, one technical note here is that I used a right Riemann sum for this. You can just as well use a left Riemann sum. This summation will change slightly, but you get the same result for the integral because n is going to infinity anyway. And so any minor differences in your Riemann sum isn't going to make any difference at all when you take n to infinity. So that'll be it for this video. I'll see you guys in the next one.